Okay, I want to just wrap up a little bit more on example one and really get after this question of why the heck did I choose this strange substitution in the first place? It worked, but why? So remember, the whole key issue was trying to deal with the square root. That's really what's nasty. We got rid of the square root actually through a Pythagorean identity, right? You see down here we ended up with this cosine of theta, and because it came from a square root of cosine squared, which was really a Pythagorean identity of the 1 minus sine squared. Okay, so what we did is I really was trying to make a substitution that would change inside the square root into a Pythagorean identity. Okay, the other thing is I had to deal with the fact that I had 25 sitting here, and I needed to get the number out. So I somehow had to make this x squared create a 25 so I could factor out the 25. Well, that means a 5 squared would do it, right? So that's where the 5 comes from. And once the 25 is out of there, then I'm going to have 1 minus something squared. Well, 1 minus sine squared would become our Pythagorean identity. So that's what worked. That's why we chose this substitution. So I want you to think about that as we look at this next problem. And here we're integrating the square root of 4 minus x squared. So we're going to do again an identity, a substitution that will make use of a trig identity. Okay, so because of the 4, I need something that's squared that's going to give me a 4. So that'll be a 2. And so when I get rid of the 4's, I'll have 1 minus something squared. Once again, 1 minus sine squared. We'll do it. Sorry, I don't actually want to put in a squared here. I just want 1 minus sine of theta. And again, that is going to be an angle substitution here. So in addition to the x, we are going to need a dx. So our derivative, 2 cosine theta d theta. And so let's put that in there. So this becomes an integral of the square root of 4 minus x squared. So if we square this, that's a 4 sine squared theta. And then the dx becomes 2 cosine theta d theta. So now let's look at the simplifying here. So we have a 4. The square root of 4 can be pulled out. And then we have the square root of 1 minus sine squared theta left over times 2 cosine theta d theta. And so, well, square root of 4, I think we know that one. And here, so now 1 minus sine squared theta is cosine squared theta. And so let's just put a few things together here. So the 2 times 2 is a 4, comes out front of the whole thing. The square root of cosine squared is just cosine. So we have a cosine from here and another cosine here, leaving us with a cosine times cosine. And now we have a trig integral that we should be able to solve. I'll use that half angle formula that says a cosine squared of theta is 1/2 plus 1/2 of cosine of 2 theta d theta. So that's just that half angle formula. And we know the antiderivatives here, right? Antiderivative. Now I wrote it again. Antiderivative of a half is 1/2 theta. Be careful, it's not x. Antiderivative of cosine will be a sine. We keep the argument to be the 2 theta still. And then the 1/2, we have to counter this 2 from a chain rule, so it becomes plus 1/4, and then plus c. Okay. And you know what? Let's just multiply that 4 through. So we have 2 theta plus sine of 2 theta plus c. So we did the integration. Now we have to, put our substitution information back in. 2 things with that. Again, I want to remind you, I don't want you just plugging in, solving this for theta and then plugging it in to the trig function, because the sine of 2 times it'll be, yeah, it'll just be junk. Okay, it'll be sine of 2 times the arc sine of x over 2. I don't want that. Okay, that's just not a good answer. And actually, because of some restrictions with some trig stuff, yeah, you just don't want to do that. Okay. Now, on the other hand, the theta we have sitting up front here, there is nothing else. It is just theta. So I actually do have to solve it in that case. Okay. So, you know, solving, I'm going to write this down here again. So our substitution was x equal to sine theta. So if we solve that for theta, right, we're going to have the arc sine of x over 2 is theta. So that actually is going to go in that spot. Okay. This spot, though, we're going to fix up a little nicer here and do it with that triangle piece. So let me put in a triangle. And so, hold on a minute. Okay, so the triangle here, it's a right triangle. Put theta in there somewhere. And so we know that the sine of theta is x over 2. That's opposite over hypotenuse. Now, if you look and say, well, wait a minute, we don't want the sine of theta. I need the sine of 2 theta. Well, what do I do there? Well, back to some trig identities. The sine of 2 theta, the double angle formula, is 2 times the sine of theta times the cosine of theta. So I can use this triangle. I do know what the sine of theta is. In fact, that was my original substitution. That's x over 2. So we're going to have 2 times x over 2. Cosine theta, well, in our triangle, we know the cosine is going to be adjacent over hypotenuse. How do we get the adjacent? Through a Pythagorean theorem. And so Pythagorean theorem, that'll be 2 squared minus x squared. Not a surprise that we got that again, because that's what was in the original problem. So our cosine, square root 4 minus x squared, all over 2. And so this whole thing simplifies a little bit here, right? We get x times the square root of 4 minus x squared over 2. So what we've done here is this piece here goes in for our sine of 2 theta now. Okay, so our final answer, as crazy as this is getting here, so we have our 2 times the theta, which we said we had to actually put in the arc sine. So it's 2 times the arc sine of x over 2. Okay, plus our sine of 2 theta, which we have this now, x times the square root of 4 minus x squared over 2 plus c. Not pretty, but it works. Okay, so notice when dealing with these square root things, we're looking for, hey, we want to make a trig substitution to take advantage of a trig identity to get rid of the square root. And then at the very end, to clean it up, we do have to do this putting together a triangle that represents our trig substitution to get it back in terms of the x terms. Okay, we'll do one more example in another video.